Well, good afternoon, and it's a pleasure to see a lot of familiar faces here again at this event. It's been several years, and I think we're all getting to know each other, and I think the speakers are too, because we're reinforcing comments right and left throughout the day. So when you're late in the day, you're going to see some things you've probably seen before. But the title of my talk this year is Storage Outlook. It's also the subject of a book that I released earlier in the summer. It's available on my website at horizon.com. If you want to download that, it's yours. It'll have a lot more than what I'm going to be able to talk about in this session today. But I want to talk about storage demand and a little more specifics than maybe what we've been used to. But let's get some numbers behind what we know are huge growth terms in our industry. First of all, we've got a worldwide population that just hit 7.4 billion people. These are the information generators. These are the people that we turned into photographers with cell phones all over the world. Everything that happens in the world today is captured on some kind of film or video and stored somewhere. It's amazing. 3.6 billion internet users, just about half the world has internet access now, and 6.8 billion mobile phone users. Just to give you an idea how many people are in this data generation thing. We talked about the digital universe doubling every 2 years. I know Nathan hit that pretty good. But what we know is about less than 5% of that data is ever touched again. So why are we storing that data? Do we need the data? We just heard just a few minutes ago that a lot of that data is useless data, and it really is. So we've got a real challenge here in what we do with data. We're going to get encouraged to start managing data going forward, or we are going to have a mess of colossal proportions like we've never seen before to deal with here. Nearly 20% of the corporations in the world today are 1 petabyte or bigger in data. That includes disk and tape together. And a lot of data that's on disk, by the way, is the same data that's on tape because it's backed up. So we're double counting a little bit in that whole number, but that's how much data is really there. Automobiles built this year, 14 million lines of code. I own a German car service business in Boulder, and when somebody drives in, the first thing we do is take a USB port, plug it in, and start doing computer diagnostics. It's not a grease monkey business. It's a high-tech computer business now to do computer diagnostics. Look at all the air codes, the checks, everything that's done. The emission control code is amazing. The autonomous cars that come along are going to dwarf those kind of numbers. Can you imagine running Windows in your car, or Linux in your car more likely, and trying to get this thing to work? And you just don't reboot when it doesn't work. But that's probably what's going to happen. But we've got a lot going on with this whole thing. The photography binge is unbelievable. We saw what anywhere between 10 and 90% of anything on the internet's a picture of a dog or a cat, but it's not that much, but it's a lot. But if you took all the photos taken in 2015, over 1 trillion photos, it would stretch 1.1 round trips to the sun, out and back 1.1 times. So that's pretty good on a 4x6 photo if you printed those off. We've got photography fever like you've never seen before. The Internet of Things is staggering also. There are estimates all over. We don't know what it's going to be, but 25 billion things on the Internet by the year 2020. Do we need all these things on the Internet? Is this demand-driven? Do you build it and they will come? Why is this happening? Do you need your refrigerator on the web? Do I want to know what's happening to a carton of milk I've got out in Boulder, Colorado, where I live? I really don't, but that's kind of what we're building to. And it's going to generate data. It's going to generate bandwidth requirements, and it's going to become a concern. And sooner or later, it will morph into something meaningful for all of us. About 75% of all the data in the world is generated by individuals. And about 80% of that's going to wind up back in a big data center, some kind of cloud data center, something you outsource to. The old service provider model, of course, reincarnated itself as the cloud industry, and it's back today. So large data centers are kind of becoming a bigger focus than they had been in the past. How about 5.75 million new servers installed every year? The average lifespan of these on the computer room floor, about 3 years on a server, about 4 on a disk. About 8 years for a tape drive before they're replaced or they fail, or they're just upgraded because there's something better that came along with that. And Nathan hit this real good earlier, and it's been a real concern of ours, I know, this year, but the HDD shipments were 150 million a quarter just 3.5 years ago. Now they're down below 100 million a quarter. So the HDD industry has given a lot up to flash, particularly at the low end where the unit count and volumes were. But this trend is well underway and continuing, and we're going to dig into that in a moment a little bit deeper. 90% of the internet traffic, if not more, is unwanted material. Surprise, surprise. We know just exactly what's going on every time we get on the internet. You want to look at something, and you're blown away with ads before you can ever get to what you're looking for. So we've got a challenge here with the internet traffic, unwanted material. If that wasn't there, what would that do to reduce the storage demand and the bandwidth consumption going forward in our industry? So there we go. But we've got a real challenge here with this. And I loved Nathan's comment about the human genome at 600 gigabytes. Wow, what a deal. When we get implants when we're born, it's going to go up, okay, say the least. Another thing we've been looking at too, and again, we've seen a couple of looks at this, but you know, how much data is really stored? Data generated is one thing, but data stored is a very, very different thing. So we all go back to that digital universe study that was famous. It showed a 44 zettabyte demand in 2020, showed a doubling of data roughly every 2 years. That's data created. But what's really stored? Well, about 42% of all the data has a duplicate copy, at least one copy. Some have many copies. We all send our presentation into Rich at Fujifilm. He makes 100 copies and sends it out, and there's 100 times the original copy. So that's a lot of duplicate data that goes in there. So we're going to go after that with deduplication. How about a third of the data is uniquely compressed? I put 2 to 1. It could be 2.5 to 1 today, depending on the technology. That brings it down further. About 5% of the data is transient data. You log on to a computer, you do something, you get off, and that data is come and gone. The temporary internet files that we love to delete because they clog up our computers are a great example of that. So this is temporary stuff. It doesn't incrementally accumulate. It comes and goes, and kind of keeps a static level there. So when you take all of these things out and look at what really happens here in the terms of total data generated, this turns out to be about 57% of the data generated by this model, and you can plug in your own assumptions if you don't like these. But about 50% of the data that's generated actually results in a storage requirement. So keep that in mind, but we're not done with this story just yet. So we've got this trend underway now to very large computing data centers. The high-performance computing market is huge. They're pushing exascale requirements right now. They're at petascale levels today. The largest HPC computer that we can identify is 33 petaflops. You get to exascale when you hit either 1 exaflop, 1 exabyte, or you do over 100 terabytes a second data transfer. Those are kind of the thresholds to call yourself exascale data centers. But we do have exascale tape libraries today. So tape is the first one to enter the exascale world of storage capacity. Faster solid-state storage for this HPC world is needed. I've talked to several HPC sites just in the last month. We had another event in Long Island a few weeks ago, and they are burning flash memory chips like you would not believe. Flash is not good enough for this market. We talk about how fast it is, but in this market it's not. And there's a long way to go with that. And Oak Ridge here, and I talked to Quinn yesterday, you can talk to him, but I think they're working on a 200 petaflop computer to come out in about 1.5 years to 2 years. But in any case, exascale requirements are going to arrive. The HPC market is pushing that, and if that's not enough, we now have the hyperscale data centers, and they are here in a big way. Some of these are as long as 5 or 6 football fields. They are enormous. There are no number of boundaries on it, but they are enormous in size. Petabytes way beyond the exascale, exabyte level, exponential increases. Most of this is homegrown technology and architecture. You see a lot of DAS, direct access storage here with this, and data replicated as opposed to RAID, replication, and redundant algorithms for reliability and availability like that. It's just duplicated muscle power hardware. So a lot of duplicate data in this. In case one fails, the workload just rolls over to another server at another location, and away we go. So you built in enough redundancy, and you have enough money to make these things really work like that. Typically, these hyperscale data centers serve millions of users, but don't have that many applications. Again, not a lot of redundancy. You know who they are. They're big. They're in the news. They are leading the way here. And Amazon Web Services, Microsoft, IBM, and Google, those 4 companies collectively control more than half of the worldwide cloud infrastructure. We have over 200 companies today in North America in the cloud business, and we have 4 that get over 50% of the entire market. So you can look at the skew in that. We have unprecedented energy consumption. These data centers are going to consume energy in a big way. You can take a look at what your energy infrastructure could look like, and you'll need a GPS and a couple of maps and a few more things to find the hot and cold water and some of these things. It's enormous. We have got an energy issue that's staggering, to say the least. And this IT energy consumption thing is actually a subject of a paper I'm working on right now. But we're looking at the energy estimates. In 2013, the IT industry used 91 billion kilowatt hours. Projections by 2020 were 140 billion. But when I dug into those, we didn't have any accounting for cloud, big data, the Internet of Things to add on top of this. So we now have an energy challenge. And who's really addressing this? A good friend of mine works for an energy analyst company in Boulder, Colorado. And they haven't even thought about this yet. And their clients are the energy providers in North America. So we've got a whole issue here with energy with this. I don't know where it's all going to come from. But if you're looking at adding another line on this chart to go up, what's the HPC, exascale, and hyperscale customers going to do to this? We have about 500 customers in the world today that identify as HPC. And the line between enterprise and HPC blurring a little bit. But the high end, with the trend for fewer data centers and much larger data centers is well underway. One hyperscale data center replaces maybe 1,000 or 2,000 smaller data centers. So we've got a whole different profile here. We said things are changing, but they're changing in different ways than we thought about before. The tiered storage hierarchy. Somebody said you would never see a talk, certainly from me, without a pyramid, and you never will. Since I've lived on this pyramid since the Egyptians did the first one. But anyway, if you look at today's tiered storage hierarchy, we do talk about 4 tiers of storage, managing that with some type of HSM, HPSS. These are old tools. They've been refined. They run all the time. I would love to see an HSM or an HPSS, a solid-state version of that in its own offload engine and just crank away. Because the way we're going to meet this kind of storage demand is not going to be with one technology, but all of these used together. One of the key things that helps us is the chart on the left that shows as data ages, it gets older, the probability of reuse declines for most data. System catalogs, indices, directories, that's not true. But for most data, it is true. And that data then drops off in probability of reuse, and it can move on down to lower activity levels of the storage hierarchy to improve the economics of this whole thing. On the right, you see the average amount of data by tier. This is for the commercial world, not the HPC world. I've talked to several HPC clients, again, and this pyramid for them is almost inverted. Their archival level is the smallest at the top, and their biggest level is the high-performance section at the bottom because they're constantly doing routines and simulations against all of that data. They have made the archives become alive again, and that's what the big data analysis does when you're into that world. But you can look and see the average data for most people by tier. About 5% of that data is very high-performance data. So do you need flash to replace everything? You really don't, because a lot of the data doesn't generate enough I/O activity to justify it. It's going to be fine on either Tier 1 enterprise disk, Tier 2 lower cost desktop disk, or even, of course, the Tier 3 world, which is very green and tape. And also people say, what about the cloud? I had some people in the past say, well, shouldn't cloud be Tier 4? Well, of course, cloud is part of a service model, not a storage tier. But what cloud does, it uses all the elements of storage. So cloud is an option here as a service to combine all that, and the smart cloud providers certainly will be using a lot of hard disk and tape. It's not clear that the flash technology is going to mean that much in a cloud because you might access the data quick, but you still have one big challenge ahead of you, and that's the network speed. So we still can't get over that with these devices on here, but this is the hierarchy. These are the aging profiles, what data goes where. The amount of data typically on Tier 3 is 60% or more of your data is uniquely cost justified for Tier 3. If you have all your data on disk, that's fine. That means, one, you probably have a big budget, and two, you can manage your data a lot more efficiently if you chose to. So here we are with the whole model set up on that. The reason that we keep talking about tiered storage is because as data centers get bigger, this becomes more and more important. Even though the cost of storage is very low, when you get enough of it, it's not low anymore. And that's what happens. So this model, this is a simple one. You can plug in your own numbers, put in whatever you want to do with this. But in this example, there are 4 tiers listed in your leftmost column. I plugged in some numbers just for easy math. $5 a gigabyte for solid state, $1.50 for Tier 1 enterprise disk, 50 cents Tier 2, 2 cents for Tier 3 tape. Plug in your own numbers, but the relative deltas are not too far off in this example. So if you put all that data on Tier 1 disk, that would cost you about $1.5 million acquisition cost. That's not TCO. If you broke it up and did a 2-tier disk strategy, and by the way, I've always viewed tiering on disk as a pretty weak version of tiering, because just tiering based on RPMs is not a great difference on that. But that would get you to $1 million with half on Tier 1 and half of your data on Tier 2. We're looking at 1 petabyte in this example split up. If I split it across all 4 tiers and use the allocation numbers that I just looked at on that prior chart, you'll look and see that you come out about $587,000. So we went from 1.5 to $587,000 here. We had a pretty significant drop. And this is why tiered storage makes sense today. There's a great savings in acquisition cost. There's also a big TCO difference, but the point of this chart is you have to use the tape tier to really get a great leverage out of tiered storage. Tape is where the greatest delta between the levels occurs, and the more data you can get on the low-cost storage, the more financial benefit you have from tiering, and also the better TCO, mainly because the energy costs are so much different. So we're going to look at those storage tiers going right down Tier 0. We're going to take a look at the solid-state business. I was part of the first solid-state disk in, was that 1870? No, 1978. Not sure here. It seems so long ago. But in 1978, we did the first one where I worked at Storage Tech. It was $8,800 a megabyte. By today's terms, that's $8.8 million a gigabyte. How about that? Whew. Tough time. A lot of money on that. But it was 45 megabyte capacity, which would hold your time, date, and calendar for the week. Tier 0, we know, is all about performance. This is an IOPS tier on this. Its database is OLTP. The HPC burst buffer is a key app for this, but it's eating flash like mad. The all-flash arrays are common. Hybrid arrays with disk and flash together are somewhat common, but you have to be careful to manage the performance across that stripe if they're in the same LUN. Challenge there. But the interesting point here, for some of us at least, is that last year 16% of the worldwide disk capacity was the equivalent of what was shipped in flash. So flash was equal to 16% of the terabytes shipped in disk. That's how big this got in such a short time. And that's put a real dent in the disk numbers. You see how the volume of hard drives has dropped considerably on that. So a couple other things with that. Flash sales impacting hard drive sales from the desktop all the way up to the enterprise and HPC, to say the least on that. And of course, on the horizon and to your right up there is what is just now beginning to be delivered, and that's the 3D NAND concept, where cells are stacked vertically. We're going to get a volumetric efficiency benefit on that since the connectors are closer together. We're also going to see a faster access time. That's going to be good on this, and triple capacity increase to start with. These are trickling out as I stand here right now in test stacks to be looked at. So this is the next big wave for flash. This is going to be a fuel injection feature for flash for the next 3, 4, 5 years. There will probably be a price point inflection on flash right now as we slow down the 2D NAND and shift into 3D NAND. And that's going to close down some fabs and cause a little bit of a shortage here. But right now, I would expect to see, personally, we're going to see some flattening of the flash pricing in the near future because the demand is being hampered badly right now. In fact, we're going to have a supply shortage most likely by the end of this year. So anyway, this is the big thing, but this won't last forever either. We're going to have to somehow get to phase change memory beyond this, where we do not have a write problem like flash does. If you order say a 4 or 8 terabyte flash device, if it's 4 terabytes, you get another 4 with it that you don't see, that's usually used for scrubbing and cleaning and everything else behind that. I talked to a software engineer working in the flash business, actually who's in my neighborhood, and he said, yeah, I'm a back-end flash engineer, software engineer. I said, what are you doing? He said, well, we do all the scrubbing, cleaning, reallocating, and regeneration of the fatigue cells in a flash device. couple million lines of code, no big deal. But there's a lot going on in that flash device. And of course, ideally, you would not have to do all that as you go forward. The disk scenario, we just heard a real good story about what's going on with disk. And of course, Hitachi in HelioSeal has done a lot with helium. What that allowed us to do, though, is move from the standard 3-platter disk drive up to 7 platters. So we all care about hardware, and we've all been around this, but more parts, more platters, more heads, more things that can fail. You have a reliability challenge that's built into this now. More things can go wrong. The first disk drive in the world shipped in 1956. It had 50 platters in it. It was the same size as me. It weighed more than me, but unbelievable. Well, adding platters is an option, but not a good one, because we're going to see that bit error rate and the failure rate now begin to decline if we keep doing that. So the helium allowed us to compress and put more platters in the same space, fly the heads closer, but there are trade-offs in this whole situation as we go forward. Aerial density right now is about 1.2 terabits per square inch on a disk drive, but the rate is really slowing down on that. We're looking at 4, 5, and 6 gigabits per square inch on tape by comparison. Roughly, and it depends on which device and which tape you compare to, but roughly there's about 200 times more surface area on a tape cartridge to write on than there is on a disk. And the aerial density is less. You have 200 times more space. You have capacity that's absolutely unlimited as you go forward with that. One of the challenges, of course, with the hard drives that's bothered me since the mainframe days when I've studied this, it seems like forever, was the low utilization of hard drives, particularly in the non-mainframe space. 50% is a good number if you can get there. Big challenge. We've got a RAID rebuild time happening here too, which has led to something called erasure coding that might help get around that. The bit error reliability, bit error rate is good. I mean, it's far greater than disk has ever been, but it's fallen behind tape, believe it or not. It wasn't always we could stand up here and say that tape had a higher reliability figure than disk, but that day has come, and it's today, and it's happened, and it's been that way for a while. We'll take a look at those in a minute. HDDs, though, remember, they can address any type of data. This is the workhorse of the storage industry, and it always has been, and it's feeling some issues right now. So the new disk concepts that are arriving to address this have come along. We talked about helium. You saw that just earlier in an excellent talk. What helium did for that. There's self-encrypting drives out there now, so we can solve the hacker problem. You want to come in and hack, 5 or 10 terabytes of encrypted data. That's going to take a while to decrypt, if ever. To come in and decrypt a password is not going to take very long. But the more data you get to decrypt, the longer it takes. So we don't decrypt or encrypt the data much, but we do encrypt the front door, but nothing inside the house. That's kind of the way that goes. But these have not been a success in the market. I'm kind of amazed that the takeoff has been so slow for the self-encrypting disk drives. Shingled drives are out. We just heard, again, a great talk on that. But the challenge is performance on this. And, of course, erasure coding is here to address the redundancy issue that RAID can no longer do. The rebuild times are staggering. So erasure coding is another way to spread a lot of data across a lot of nodes and a lot of locations. This is great at hyperscale speeds, but you can't take 4, 5, 6 days to rebuild a failed disk drive in a RAID array today. And as disks get bigger, the rebuild times get longer, and that's a real challenge here. And of course, HAMR is another technology here. For me, HAMR is the technology of the future, and it always will be. It's kind of like holographic storage. I had one of these crystals when I was a little kid. I still got it, and it's still a technology of the future. But a lot of these, there's a lot going on in disk, but it's there to deliver help for the challenges that disk faces. But none of these things that disk is looking at right here address performance. The IOPS are not changing. This is all about capacity, rebuild, reliability time. So we have a challenge in our industry now. There's always something out of whack. If it's the network speed, if it's the storage speed, or if it's the compute speed. Right now, of course, the I/O speed is falling way behind compute speed in our equation, and farther behind that is network improvement. So these are real issues here. So what's on your disk? What are we doing with this disk drive? Let's take a look and see what's on the typical non-mainframe disk. It's very different on a mainframe. But on a non-mainframe disk, about 5% of the space is overhead control fields. Another 5% are unknown files, orphan files, virtual machines that nobody knows who they belong to. People leave the company, their files are still out there. About 40% of that data is really live, good data that we know, we have an idea what it is, and 20% of that is allocated but unused. Somebody owns it but never used it, and the rest of it is just inert free space on that. So we've got this challenge here to take a look and see what's in this whole space. And let's classify that 50% of that data by its value. About 15% on, these are industry averages, so you can use your own numbers. But this is to get you in the ballpark and started with a process. But this is if you did everything across the industry, most likely what you would see. About 15% of that data is mission critical, another 20 vital, 25 sensitive, about 40% non-critical. The definitions are here. And sadly, what we see is, amazingly, that a whole lot of that data actually is not secure. Estimates are about 40% of the top two tiers, mission critical and vital data, have no security measures effectively behind them at all in our world. So hackers have a great day. It's your lucky day because security is a suggestion. It's kind of like a stop sign in Italy. It's merely a suggestion. Time to get serious about this. In the tape scenario, we've had a lot of things happen here recently. In fact, over 85% of the tape drive shipments are LTO today. There's been 100 exabytes plus of LTO shipped. We'll update that a little later this year for the Tape Storage Council on this. Barium ferrite driving a lot of immediate progress on that. Mentioned a few of these things before about bit error rate surpassing disk, and of course a 10 terabyte native, 25 terabyte drive today on its way up. A lot of things here are about capacity in tape, and you know, this is a tape event sponsored by a tape company, but I'd love to hear about 220 terabyte tape cartridges. But when we get so big, we've got to start thinking about things other than just capacity. I need to talk about data rate and access too. But it will fall into the same challenge disk has now, where they're just getting bigger, but there's no better way to access anything there. So when we increase capacities on any of these storage devices going forward, we need to have a conversation around access time and performance. So that's a key thing here. We've heard several talks today about the cloud embracing tape, and it's about time. Their financial model needs this, and we'll see that later. This comes from the INSIC paper done recently, just outstanding numbers to look ahead at what technology can do for tape. This is, to me, excellent insight into the future and what kind of technology promise we have for tape. There are a lot of things up there to look at. Of course, capacity has been the hallmark of what we talk about at these storage conferences, but I'm here to say that we need to talk about getting to the data also, not just storing it. Storing is one thing, retrieving may be everything. So let's talk about that. And I highlighted the data rate here on tape for us because look at these data rates, 22% a year compounded annual growth rate for tape data rates. That is really good news because we need a lot of data to move. And if we want to move that data, maybe something's going to help us on the tape side. Tape data rates, as we saw earlier, are much faster than the raw data rate off of a disk drive, 2.5, 3 to 1. And a concept that's time may have finally arrived. It has been around for 20 years. I know I worked on it 20 years ago. But it didn't work then very well because the tape drives didn't have much buffering, so you had to keep everything synced mechanically. But now with the 2 and 4 gigabyte buffers in every drive, you can mask off all of that physical issue behind that and sync these drives and let them go. And in this example of rate 5, which is redundant arrays of independent tape, we're going to multiply that data rate. We're going to put parity on drive 1 and spread it across and rotate it around the drives. This is a stripe 4 wide for tape, tape rate. Again, Quinn at Oak Ridge can talk to you about their experiences. They're doing it actually right now, a very interesting example. But this is going to be what is going to be needed to talk about gigantic capacity tapes in the future. We will never get anything off of this stuff. So the time is coming for rate. 20 years later, first time didn't make it, second time will make it. We've seen people begin to use this already. There's some overhead with that. The parity does take some space on that, and with that you get a big multiplier on data rate. So another glimpse into the future, I love to do this now once I finally figured out it meant something, was to start looking at the patents in the storage industry, and there are thousands filed, but I just listed a few up here from Oracle, IBM, Spectre, and Fujifilm, for example, in the tape space to look at what's happening here. You can scan through these for the sake of time. I won't go through all of them, but look at things that are titled solid-state tape storage media. Now, I don't know what this is. It's a patent, so it may not come to market. But if these things do come to market, we're going to be in for some pretty good times here in the future. I always wanted a tape cartridge that had a flash memory chip in it that looked like a VTOC on a mainframe disk. It would tell me exactly where to go on that tape to find something, and I could get away with this big issue of searching for 2 or 3 days to look for something. Even with partitions today on tape, there's still a challenge with that. So high-performance cartridge format, solid-state tape with this concurrent access for hierarchical data storage. How good is that? Write it to disk and write it to tape concurrently. These are future enhancements for HPSS and HSM that need to be integrated with the hardware system. There's a lot of vision here. It's not just about capacity. And that's the key point I want to make on this whole chart. Well, I have to mention optical disc. Again, somebody once said there's been more written about it than written on it, but whatever. That's not true. You find optical disc in your home and in your car, but in all honesty, it's not a very good data center technology. It's fallen so far behind magnetics in price, performance, capacity, reliability, and data rate that you have to think twice about just how you put it in the data center. Today's Blu-ray, well, in fact, let's look at the market share. CDs are about 35% of the whole optical market, DVD 50, Blu-ray disc about 13%. You know, at 50 gigabytes and a 6 terabyte LTO7 cartridge, we can put 120 discs on one piece of tape media. So the media handling alone ought to get you concerned. How about the bit error rate at 1 times 10 to the 12th? That's another issue that's far below all the other technologies. The worm technology is more reliable than read-write, so now you got to be a little careful about what goes where. The bottom line is this is really fallen way behind magnetics in terms of capacity, in terms of really every feature on that. The Blu-ray disc roadmap is over here, but even if it stays on this roadmap, the disc roadmaps we just saw all day long and just a minute ago for tape go up much faster than this. It's going to fall farther behind even if optical can adhere to this roadmap. So the challenge is set. I think it's going to be a great entertainment technology, but in the data center that's going to be tough. If you look at the reliability levels that we have for all our available devices, you start at the bottom. The Blu-ray's 1 bit in error and 10 to the 12th bits read. It's up to 1 and 10 to the 19th for enterprise tape. Flash 1 and 10 to the 17th, slightly higher than the best disk drive today. And I think we'll see 1 and 10 to the 20th imminently in the disk space here, coming up very quickly. So media life is good for the removable technologies, and they're going to play a big role as we go forward here, because we've got to do some different things about backup and archive and how that works. We saw at least once today talk about backup and archive, and they are not the same. I am still amazed at how often this issue gets confused. But backup, we're going to copy files. We're going to copy them off to disk. We'll make another copy off to tape, maybe remotely somewhere else, geographically remote, so we have, in case of a failure, another one to get. If we go down and look at archive, we have the same files on the disk, but they're not used much, but we still need them. We're going to archive them. We're going to move them. We might move them off to a tape archive, maybe another tape archive to keep 2 copies of it like that. I love the active archive concept, which we have not spoken about in this event as of yet, but that's a disk array really in the front end of tape libraries to keep that active data for 2, 3, 4, 5 days, maybe longer, and before it migrates off to tape. And then you can do your re-referencing based on the probability of reuse off of that disk. And then the files are gone, and the space is freed up. Archive frees up space. Backup creates more data. So archive, we're going to move it somewhere else, free that space up. It doesn't need to be there. It's like taking that sofa out of your living room you haven't sat on in 10 years. Let's put it up in the attic, get it out of here. We didn't get rid of it. So that's kind of the difference of backup and archive, very different. And archive is the swelling piece of this equation because we have to keep so much data so long now for all the legal issues that are here. A survey done by SNIA recently showed that, amazingly, 50-year retention was required by over 57% of the people to keep data 50 years. And now you can see it's probably going to get bigger than that. I've got a chart here for you. I won't go through it. It lists the comparisons of the key archiving functions and comparing tape to disk. That'll be in your in the slideshow. You can look at that and see what stacks up best for archive at this point. And it's all there. And of course, when we look at the cloud here and tape in the cloud, we've got to start getting a little more serious about what's going on here. Just to throw everything up in the cloud and think it's cheaper may not be exactly what you think it is. And let's look at a 20 gigabyte file. If you packetize that for TCP/IP, that's going to put about a 40% overhead on that for framing. That's going to turn out to be about 224 billion bits of data. If you encrypt it, that's another 10 to 15% overhead on those packets. Typical storage price, 2 3/4 to 3 cents a gigabyte per month. Most storage prices are over 36 months, so if you take that out to what we do with all our other comparisons, 3 times 36, that's $1.08 a gigabyte by comparison. Don't confuse monthly with total purchase price. Transfer price is 2 to 9 cents a gigabyte, or 20 to 90 cents a terabyte. One thing to keep in mind, the more data you move, the more you pay. It might be cheap to store data in the cloud, but you start moving data in and out of there, link it up to your bank account. Okay, we're going to do some electronic fund transfer and let it go here. And that's why high-performance data and OLTP is not really a very good candidate yet. It's very expensive to move data in and out of the cloud. It's cheap to store it there. That's good for archive. But OLTP doesn't have a play there yet, unless you can suffer very long response time. So 224 billion bits at 1 billion bits per second, and this model gives us this kind of set of numbers here to look at. I have several file sizes to choose from. Again, a model, use your own. 20 gigabyte, 1 terabyte, 10 terabyte files at 1 gig, 10 gig, and 40 gig E, if anybody has that. And you can look at 1 gig E to do a 10 terabyte file. That'll take you 1 day, 7 hours. If we move it on up to 10 gig E, it's 3 hours and 6 minutes. That's for 10 terabytes. How about a petabyte? That's 100 times that. That's 100 times 3 hours. 300 hours, that's almost 2 weeks to do that. So what are we going to do here? That's unacceptable. How much data are you going to seed the cloud with? How much data are you going to put in there? What's going to happen with this whole scenario? The biggest cloud challenge today is limited internet bandwidth. So in this example, this is one of the great roles, I think, for tape going forward in the future. Nathan hit on it with Black Pearl, of course, which he's got set up very nicely for this. But a cloud gateway links everything in your data center, and you're going to put something off in a cloud, either on-premise in a private cloud, and that gives you a single organization, single occupancy, so you don't have to share resources, or you can go over the internet, use some type of gigabit interface that we just saw, likely S3 for the object storage, and move that out there. But what if you're taking 4 or 5 days or a week or 2 weeks to move it over there? There's a quicker way to do that. Why don't we tie that to the tape drive to that internet gateway, keep a copy of that on tape, which will go over there very quick, and as soon as that happens, something happens or it's too long to bring it over across that network interface to the cloud, why don't we just put it on a truck and move it over there? Overnight bandwidth on a truck is much, much faster than on the internet. So the truck access method, and I spent a large portion of my career trying to get rid of the truck access method, I can tell you what, it's here to stay. It's faster than our networks for large amounts of data. You have to do the math, but it's a real challenge to do that. So in conclusion, we are in a dynamic change, and it's not just about capacity and feeds and speeds, but the whole data center world is changing. Everything's changing. As we look at the storage equation, you see the SSD tier becoming a bigger piece of the total storage pie, and the tape piece becoming a bigger piece. And we've already seen the hard drive business give up 50 million drive shipments a quarter in the last 4 years as it's being pressed because of all these issues. So basically, the old way was just to keep adding more disks. The new way is to optimize your storage tiers using SSD, disk, and tape. If you want to get smart, now's the time. This stuff all works. Tools are pretty well here. You can make this happen. So in conclusion, we're reshaping the future. I think that's for sure. And remember that things are changing so fast, even the future is obsolete, okay? All right. Anyway, thanks a lot.